Okay. Assalamualaikum sir. My name is Ananya Shapir Kusha. Today I will present the solution to my automatic metro crowd management assignment. The project focuses on designing a digital system that controls passenger entry to a metro platform, counts people, triggers an alarm if the maximum limit is crossed, and transmits a live analog voltage signal to the control room. I will go through all 6 questions one by one, explaining both what was asked and the detail of my solutions. The first question asked me to draw a block diagram of the automatic crowd management system including RFID sensors, an ADC, a synchronous counter, a finite state machine, an alarm circuit, and a DSC. The diagram begins with the RFID sensor since every passenger must scan before entering. The signal goes through an analog to digital converter to obtain a clean digital output. This feeds into a synchronous counter that records the number of passengers inside a finite state machine. FSM then controls whether the gate should open or stay closed depending on the counter value and ticket status. If more than 3 passengers attempt to cross at once, an alarm unit based on a 555 timer is triggered. Finally, the digital to analog converter outputs an analog voltage proportional to the passenger count, which the control room monitors in real time. The second question asked me to explain the FSM transitions between states idle, check, open, and close, and implement them in Verilog. I use two flip-flop to represent 4 states with binary codes. Idle equal to 00, check equal to 01, open equal to 10, close equal to 11. The flow is when idle, if a ticket is scanned, the FSM goes to check. If the ticket is valid and the passenger limit is not exceed, the FSM moves to open, so the gate rises. If the limit is reached, it goes back to idle. Once the passenger has passed, the FSM goes to close and then returns to idle ready for the next entry. I implemented this design in Verilog with one always block for the synchronous state register and another for the combinational next state and output logic. This ensure reliable clock-based control of the gate, and this is the HDL code. The third question asked for the Boolean equation and NAND gate circuit that produces an alarm when more than 3 passengers attempt to cross simultaneously. I labeled a 4 crossing sensors as Q1, Q2, Q0 and Q3. Since the alarm should activate only when all 4 sensors detect passenger together, the Boolean expression becomes Q1, Q2, Q0, Q3 or Q3, Q2, Q1, Q0. This represents a 4 input and condition. To implement this using only NAND gates, I designed a standard NAND configuration that performs the equivalent AND logic. Whenever Q1, Q2, Q0 and Q3 are high, at the same time, the NAND network outputs a signal that immediately drives the 555 timer warning of excess crowding. The fourth question required designing a 555 timer alarm circuit with a frequency of P into 5 Hz. So the summation of METRO is 18 and the frequency is 185 Hz. Since 185 Hz is not ideal, I adjusted to a practical 400 Hz using a stable mode formulas. Time period equal to 1 by f, which is 0.0025 s. Time high equal to 2.05 ms. Time low equal to 5.5 ms. I connected the alarm signal from the logic to the reset pin, so the siren only sounds when crowd overflow is detected. Here we choose 50 microfarad capacitor because it gives largest resistance among these three. For this, there is a convenient amount of currents and no power is wasted here. The fifth question asked me to calculate DAC output voltage for passenger counts of 5 and 10 using a binary weighted DAC with a 5 volt reference. Here we can use binary weighted DAC or 2 or ladder DAC, but here I used binary weighted DAC with a 5 volt reference. We know V out equal to V by 8 plus V by 4 plus V by 2 plus V by 1. For decimal 5, V out equal to 5 by 2 plus 5 by 8, which is 3.125 volt. For decimal 10, the binary is 1010 and V out is 5 by 1 plus 5 by 4, which is 6.25 volt. Thus, the DAC output voltage increased with passenger count, providing the control room with a clear analog signal representing crowd size. The sixth question asked about the limitation of the system. I mentioned 4 key points. The system has fixed limits, only 10 passengers allowed on the platform and only 20 tickets issued per day, and changing this requires reprogramming. The design relies completely on the RFID and crossing sensors. If a sensor fails or if 2 people cross at once, the count will be incorrect. There is no backup power or controller, so any fault or power loss stops the system. Fourthly, communication with the control room is limited to a signal DAC voltage without detailed ticket or passenger data. Finally, future improvement could include redundant sensor, encrypted RFID cards, a digital communication link, and emergency override system. Authority should install some camera-based backup or infrared backups to make this system more reliable instead of using the simple DAC voltage at any digital communication. In summary, this project integrates RFID detection, asynchronous counter, FSM control in Verilog, NAND-based alarm logic with Q1, Q2, Q0 and Q3, a 555 timer alarm circuit and a binary weighted DAC to form an effective automatic metro crowd management system. Each question's requirements, whether block diagrams, Boolean logic, Verilog code or calculations, are addressed with complete solution. Thank you for listening to my presentation. Assalamu alaikum.